All right, if you think back to the kind of the beginning of this chapter, we wanted to basically find a potential energy version for chemical potential. What is this energy? What does it mean? And we found what it was, and we said that if a reaction is spontaneous, that the entropy of the universe is increasing, right? Greater than zero. If it's non-spontaneous, then it is decreasing, right? So we found those rules. However, it's kind of not that satisfying of an answer, because every time we want to think about whether something's spontaneous or not spontaneous, we don't want to think about the universe, and we don't even really want to think about the surroundings. We want to just talk about the system. So let's see how we can do that, and it's through this new measurement called Gibbs energy or Gibbs free energy. Cool. And so if you start talking about, delta S of the universe is the delta S of the system plus the delta S of the surroundings, we can then say that the delta S of the surroundings is equal to negative delta H of the system, right, over T, as we saw in the previous video. So plug that into here. Cool. And then we're going to multiply both sides by negative T. So you get negative T delta S of universe is equal to negative T delta S of the system minus T here, delta H of the system. These guys can go ahead and cancel out. And then we're going to just go ahead and call this negative T delta S of the universe as delta G, or Gibbs free energy. So at the end of it all, delta G is equal to delta H minus T delta S. So this is the change in Gibbs free energy. And we'll talk about why it's kind of called free energy later on, but you can think about it's equal to the amount of energy being released by the system, and then how much energy that's released is lost to the surroundings in terms of entropy. But we'll get into that later. So this is in units of joules, right? This is change in enthalpy. So we can think about that as heat, and that's in units of joules as well. This is temperature, obviously, and it must be in Kelvin. So that's units of Kelvin, obviously. And then delta S is the change in entropy, right? And this has units of joules per Kelvin. So you can see the units all work out. And so you can see whether something is spontaneous or not depends on the relationship between the enthalpy and the entropy of the system. Some things are going to favor it, some things are going to disfavor it. We'll go into kind of a different video into why later. But there's another big point that needs to be pointed out here, right? So if delta G is equal to the negative T of the delta S, they're going to be inversely, or not inversely proportional, but they're going to be opposite signs. So for a spontaneous reaction, the delta S of the universe is positive, but the delta G is negative. So if you have a spontaneous process, you have a negative change in Gibbs free energy. And the opposite, non-spontaneous, means that you have a positive value of Gibbs free energy. So you really want to know this along with the universe one as well. So be able to know both. Delta S is positive, negative. What does that mean? Delta G, positive, negative. What does that mean? And delta G right here is can be thought of as our kind of chemical potential. It's not totally right, but it's pretty close. So we can think of that in terms of our chemical potential. So if we go back to our analogy, that we watched kind of, I think, in the first video. You might want to go back to that. We said, you know, if we have a ball right here and we place it right here, over time, it's going to go down. The ball is going to roll down, and eventually the ball is going to end up here, right? It ends up in lowest potential energy. Well, we can think about a reaction right now and say, let's A in equilibrium with B. And here, instead of potential energy, we call this Gibbs energy. That's our kind of chemical potential. And this here is our reaction progress. And then the two kind of ends of our hills will be like A and B, right? On one side, we've got A, on the other side of B. And just like if you had called this hill A and B, right, the lowest energy point is actually going to be somewhere in between, So if you start a reaction here, it's going to go down, and then the reaction will eventually end up here. And if you think about what this x-axis means, on this side we have all products, on this side we have all reactants, and then we had a quality of products over reactants, right? That was our Q slash our K equals products over reactants. And so this side is Q going towards infinity. This side is Q going towards 0, right? And right in the middle, right where we end up, this is where our Q is equal to K. So you can see that the Gibbs free energy is kind of the Y behind what value K is for a certain reaction. And the reason the K is that value is because it's this local energy minima. And in this case, our x-axis here is Gibbs energy. So just a real quick quiz, spontaneous or not? Delta G equals negative joules. Delta S of universe equals 10 joules. Delta G equals 10 joules, or delta S of universe equals negative 10 joules. So go ahead, pause the video a little bit, tell me which one's spontaneous, which one's not spontaneous. Cool, so you got to remember that the relationship is delta G equals negative T delta S of universe, and so they're opposite signs, right? So something is spontaneous if this is positive, and so that means it's spontaneous if this is negative, right? And so the first one we see delta G is negative, that kind of fits over here, and so this is spontaneous. Next up, we have delta S is positive, delta S of universe is positive, so again, that will be spontaneous. Next up, we have delta G is 10 joules, so it's spontaneous if delta G is negative. So if delta G is positive here, this must be non-spontaneous. And then again, if delta S of universe is positive, it's spontaneous. This one's negative, so it's non-spontaneous. So just know, you know, delta S of universe must be positive to be spontaneous. Delta G must be negative.